All right, momentum is mass times velocity. So if I have a balloon and it's moving with a certain velocity, its mass times the velocity is the momentum of that balloon. Now, if that balloon stops, that means the velocity went from whatever it was to zero. Its change in momentum is the momentum that the balloon has right before it stops minus zero. So this balloon has a certain momentum. It hits the kid and blows up. Its momentum is now zero. Now, to change an object's momentum, the change in momentum equals the force times the time. That's called impulse. Impulse equals change in momentum. So, if this balloon has a certain momentum and you're going to bring it to zero, you can do that with a big force and a small time, or a small force and a large time. The longer you make the time, the smaller the force. If you do it in a short time, that's going to be a big force and the balloon will break. You want to take care of that momentum using a force and a time. Here's what happens if you extend the time. You extend the time and decrease the force. Let's try that again. Two different ways to stop the momentum of this balloon. There's two different ways to stop the momentum of this balloon.
I have one way.
One is with a small time and a big force. Another way is, here, catch this one, a big time, big T, small f. Either way, you get the same change in momentum. Did you drop it? All right, let's try it again without dropping it. You ready? He moved his arm with it, extending the time and decreasing the force. And that is known as the impulse-momentum equation.
All right, go get me now.
And now for an experiment in impulse momentum. By increasing the time of impact, you decrease the force. Go. Did you hit play?
Go!
I'm going to increase the time of the impact and decrease the force. I'm back with another demonstration of the impulse momentum equation. I'm going to be taking this egg. I'm going to throw this egg and it's going to have a certain amount of momentum. In order for this egg to stop, the change in momentum is going to be the same, whether this egg is stopping because it's hitting a sheet or whether it's stopping because it's hitting a tree, which we're going to demonstrate afterwards to show you this is a raw egg. The change in momentum of this egg to bring it to a stop, the mass times velocity, the change in that mass times velocity is equal to the impulse, which is the force times the time needed to make it stop. Now, if I drop it onto the floor, that impulse is going to happen over a short time with a force large enough to break the egg. But if I throw it at this sheet, that time's going to take a little longer because the sheet moves, and that decreases the force to the point where the egg does not break. No matter how hard I throw the egg at the sheet, it is not going to break. You want a shot too? All right. Thank you very much. Now come over here. Now, when it hits the sheet, it's brought, the momentum is brought to zero because of a large time and a relatively small force. If I take that same egg and I throw it at a tree, that's going to cause the time to be smaller and the force to be greater. In both cases, though, the force times the time is the same. The difference is one has a greater time and a smaller force. That's the sheet. The tree has a smaller time and a greater force. Are you going to be able to hit it from here?
Yeah.
All right, let's see.
Nice.
There you go.
That was a good hit.
Impulse momentum. This is part of a continued lesson about the impulse momentum equation. You can stop something with a big force in a small time, or you can stop something with a small force and a relatively larger time, like the difference between hitting a tree and a sheet. So Skylar was wondering what would happen if we threw the egg at this rebounder. Would that increase the time enough to stop it from breaking and decrease the force? So let's find out. Let's talk about types of collisions. We're just studying momentum. Two types of collisions. There's elastic and inelastic. So let's take a look here. All right. So I got a tennis ball. I'm gonna take this ball, and this is not a perfectly elastic collision because nothing really is. There's always going to be sound and heat produced. But I can take this tennis ball and I drop it, and it bounces, as you can see. That is an elastic collision. Now here we go. You ready for an inelastic collision? We take this squishy ball. Now that is inelastic collision. We're here to demonstrate the impulse momentum equation by acting out an inelastic collision with this medicine ball and the boy on the skateboard. Here we go. All right, we're still testing out momentum. So we have the system, which is the boy and the medicine ball on the skateboard. The boy's going to throw the ball to one side, and we're going to see what happens to the boy. Now, throw it as hard as you can in front of you. And he moves the other direction. And momentum is... I am here to talk to you about momentum, like we've been doing. Now, this next demonstration has to do with momentum as well as energy. You can talk about it in terms of either one. So first, what I want to do is take this baseball and just drop it and let you see what happens. All right, we get a little bounce. If I take this soccer ball, that's what happens. Now, if I put the baseball on the soccer ball and let them fall together, observe what happens. All right, so we got to think about what's happening in terms of momentum and energy. This can work thinking about conservation of energy or conservation of momentum. On the way down, they're falling as one system. The baseball soccer ball system. They have a certain amount of momentum. They have a certain amount of kinetic energy right when they hit the ground. All right, now a little bit of energy is going to be lost to heat like it always is, but that's just a little bit of it. Once the big ball stops, all right, the baseball is what's moving. So for momentum to be conserved and energy to be conserved, the only way for that to happen is for the velocity of this ball to increase. So in order for the momentum and the energy of this ball after they collide with the ground to be the same as the momentum and the energy of the balls together before they hit the ground, we have to have an increase in speed of the baseball. And that is exactly what we see. To make up for the to make up the difference and keep momentum and energy conserved, we gain velocity. All right, you pause it. All right.
So now we're going to be trying to do a triplet.
We're going to try 3. Oh, it's on the roof. It's in the gutter.
Oh!
There's a ladder for that one. All right, you can stop. You want to try some?
Yeah.